He's got it. He's got the original slide, so he'll go get that squared away. What's that? Okay, that's fine.
Chinese based in Taiwan.
I'm on the committee.
Oh, okay.
Have you been back to China recently?
I like it. I like it.
Yeah, I was there a couple months ago, and that was fun. There was no problem. Yeah. Military side. But how did they, when did they interrogate you? As you were leaving? No. Did you have the embassy involved? Did you talk to the U.S. Dorian. Yeah, it was good to meet you.
Hi, Dorian.
It's a headache. Yeah.
The ambiance of the room is really good. You hear everything.
The finalist for the climate project, and maybe for the other one too. Yeah. I haven't, Utah, I'm assuming the national. She had a bad experience similar to yours, coming into the country. And on the U.S. She was at ISC in Germany. And they reduced the number of submissions to the list. So Chinese submissions are way down. I think Lenovo's the only one that
They only report positions outside of China.
outside.
And they know what it's for one cell in China. That's the only cell we have. It's a new installation in China.
Good to see you. Good to see you. I'm still That's right.
Yes, yes. Yeah.
Sir, does it
notification. I think if you set
Yeah. We'll make sure you're paying attention. We'll look right at you.
Give me the quiz.
People to, for one of the facilities they talked about. And they didn't have a registration.
We will be getting starting shortly.
Hello, everybody. Good morning or afternoon. Close. On the button, yeah. Thank you so much for coming here today with us. I would like to introduce you to Dorian Arnold, who's right there, the SC chair, General Chair.
Hi, good morning, everyone. Welcome. So it's my pleasure to invite you or welcome you to Denver for SC23. We hope tomorrow to announce that we would have a record attendance at SC, so we're excited in every way. We're right at the cusp, so get ready to report record attendance, we hope. I just wanted to kick off with a little bit about the theme of the conference, I am HPC. Right? As you'll hear about on the panel today, you'll hear a lot about the wonderful technology that is supercomputing and that is high-performance computing. But one of the things that we wanted to also bring out in the conference is the people, right? The people, the wonderful pioneers behind computing and the beneficiaries of computing, right? We're all doing this to make the world a better place. And so with that, I hope that in your messages about the conference, I am HPC, the I, the people, and the HPC, the powerful computing, resonates throughout, and I wish you all a very great SC23. Thank you.
Hi, so I'm Christine Baissac-Hayden, and I'm the Communications Chair here at this year. As Dorian said, IMHPC is the center, so the objective is to humanize machine, make machines look like humans. That looks a little scary, right? But everything happens with the person behind it. Because of that, we created about 80 IMHPC profiles, and I hope that you discover them on our websites. With this, the plenary, the HPC Illumination Pavilion, and highlighting HPC hidden figures at the 35th anniversary will also showcase this. To bring this to you today, It took a lot of work, 29 teams, near 1,000 volunteers. New for you this year, and I hope that you take the time to see it, it's the Quantum Village, the Gordon Bell Prize for Climate Modeling, and SciNet Research Exposition on the exhibits floor. We have the media office next door for your convenience. Relax, ask questions, we're there for you. This room is going to completely change configuration. It will be the interview room, and you may reserve that as well. So today, I'm very excited to have this panel of people who are going to share their knowledge. So we're going to start with Lori. Lori's going to do exascale computing, Heather West for quantum computing, followed by Jack Wells with AI. After this, we will have the top 500, we'll go the other way, and the green 500 presentation. We will conclude with a Q&A. All right, thank you so much. Heather? No, Lori?
Whoever you are. And are the slides here? Oh, yes, they are. Hi, everybody. My name is Lori Daishin, and I'm from Lawrence Livermore National Lab, and I'm currently serving as the director of the Exascale Computing Project, and so I want to talk to you a little bit today about how far we've come with exascale computing in really the last year since the top 500 was announced about 18 months ago. So here's my bottom line. I'll say it now, and I'll say it again at the end. We have delivered exascale systems. They're on the floor, and they are performing exceptionally well. We have improved applications by factors of tens to hundreds to thousands through not only the hardware improvements that we've seen in the last order 7 years, but also through algorithmic improvements. And I'll talk about a couple of examples a little bit later in the presentation. We think one of the key benefits that we are seeing from a lot of this work is the fact by using accelerator-based computing on the architectures that the exascale computer architectures have, we're really seeing a reduced energy consumption for the applications. And that's not only helpful at the exascale, it's helpful from laptops to small-scale systems to petascale-based systems. It's going to be the entire chain of computers are really going to benefit from that. And the Department of Energy, through its investments in both the systems, the non-reoccurring engineering costs associated with those systems, and through the Exascale Computing Project, we've really shown the way to a lot of industrial partners, academic partners, of how to use these systems and the kinds of benefits that are possible. And we've de-risked it, really, by providing a software stack. So these are some of the things we'll talk about. And we've got thousands of users already benefiting from the applications that we've deployed and also from the systems themselves. So the facilities that have been deployed or are in the process of being deployed at the Department of Energy laboratories are three. The first is the Frontier system at Oak Ridge National Lab that's currently #1 on the top 500 list, and we hope it remains so. It came in at 1.19 exaflops when it was reported, and we have had access through early science programs and through the ECP since April of 2023. And so we've had access to the full system for quite some time. Even as early as October of last year, though, we had limited access. So we were able to get on the machine, test it out, and practice it. I would say that the machine is really stable right now, and it's performing exceptionally well. The Insight program is on there. All the ECP teams are on there. I think ALCC teams are on there as well. And so we're seeing a lot of different teams making effective use of this system. The next system that will be deployed is the Aurora system at Argonne National Lab. This system has completed its installation phase, and it's been installed since June of 2023. So in the last 6 months, it's been installed, and currently, as all large-scale machines do, it's going through that shakeout phase where we're, looking at any bugs in, the software stack or in the hardware, just shaking all of that out. We in ECP have had limited access to this system since July. so this past summer, and so far the teams that have gotten on it are seeing really, really good performance on the nodes. So we're really looking forward to getting full access to that system, hopefully later this month. And then finally, El Capitan will be delivered at Lawrence Livermore National Lab. The hardware is coming onto the floor now. We expect it to be deployed in mid to late 2024, and there will be a brief early science period for that machine before it's turned over to classified use for stockpile stewardship for the NNSA. So all of these systems are interesting in that they're accelerator-based architectures, and a lot of the applications and software that's needed to run effectively on those kinds of computers were not yet ready. In fact, there were reports generated, the 2010 timeframe, 2014 timeframe, that said the software can't be a second-class citizen, right? We're going to need to make a significant investment in the software to make effective use of exascale class systems. And so the Department of Energy created the Exascale Computing Project, which is a $1.8 billion project that's been going since 2016 and has really been focused in on that software ecosystem. Not only the high-level applications that we'll talk about, but also the underlying math libraries, visualization tools, et cetera, that are needed to make those applications run well. And then also the integration into the facility itself, where we had investments through the Path Forward program with 6 US computer vendors to look at technologies that were going to impact the exascale systems that are being deployed now. And so one of the things that I want to share is just how amazingly broad the suite of applications are that can run on these systems. And so with ECP, we selected 21 applications from the Office of Science and 4 applications from the NNSA that were designed to show not only the performance of the system, so we selected applications that were running well on the 2016 systems that were available at the beginning of the project, but also applications that maybe didn't have a big footprint in high-performance computing yet. So we're trying to expand the reach of high-performance computing to some new application areas such as cancer research and wind energy. And so those kinds of investments are going to make high-performance computing, we think, even more important for the nation. So I do want to highlight, for those applications that were already performing well on petascale class systems in 2016, what kinds of improvements were we able to achieve with sustained investments over the last 6 to 7 years in both the hardware and algorithmic improvements for those applications. And so these are some of the applications that, again, already doing excellent work at the petascale. And you can see they've gotten 70, 200, 300, as much as even several thousand times improvement. Not only from the hardware, which we would have expected a 50x improvement for our applications, just hardware alone, but from the algorithmic improvements as well that these teams were able to invest in. So 2 that I want to particularly highlight are here. One is focused on small modular reactors, and the objective here was to help DOE meet its goals to more cost effectively deploy these systems in a time frame that's makes sense in the next 10 years, so that we have safe, clean, and affordable nuclear power options. These systems are such that they can power small-sized towns. And so what's really nice about them is the modular stands for the fuel cores, which can be swapped in and out, and so you can amortize the cost of things like storage of these like the depleted fuel rods when they're done. When the Exascale Computing Project started in 2016, what the team was able to model was basically just the initial condition of a fuel rod. So there's 4 to 5 isotopes in there, and they could do a snapshot at initial time. With the Summit system, which was the system in between Titan and Frontier, so the order 125 petascale type system, they're able to take a snapshot of a depleted fuel in time. So it's about 5 to 7 times more expensive to do that calculation than just the initial fuel, because there are a lot more isotopes. And now with Frontier, they can actually model the evolution and track the temperature history from the initial fuel through a depleted fuel rod in ways that they could never do before. And so that's really going to accelerate their understanding of what's going on in these fuel rods and help design safe and effective fuel rods. So I do want to highlight that this is one of the Gordon Bell finalists this year at the conference, and their presentation is tomorrow morning. So I encourage you to attend that session. And then the other application I thought would be fun to highlight, because I'm in the Bay Area, and so this one is particularly relevant for me, is earthquake simulation. So at the beginning of ECP, teams were able to model earthquakes and the motion of the ground, but they weren't able to do it at a resolution that was fine enough that you could actually couple it to a building and do risk assessment. So one of the things that we've been able to do with the exascale computing project is make that leap forward. So we now have a code that is able to model earthquakes at such a fine scale that it actually makes a difference for buildings. There are engineering codes that look at, if there's a ground shaking, what is happening to the concrete in the building or the steel structure? And so where is the highest risk going to be to infrastructure, for example, in the Bay Area? Based on this modeling and simulation, you can do a lot of different scenarios and have those answers. So these are the kinds of achievements that are possible with exascale class computing. And so, again, just wanted to highlight a couple. Happy to talk to you about a whole bunch of them if you want to. And also our application leads are here, so I can also point you in their direction. I do want to point out that this would not have been possible without the software ecosystem that underpins these applications. So one of the big investments that we've made through the exascale computing project is putting together a software stack that's vertically integrated, that is tested and deployed not only on the exascale systems, but on systems across the Department of Energy, across academia, increasingly with other agencies in the US government and with academic partners. And so this software ecosystem is comprised of debugging tools, runtime tools, math libraries, visualization libraries, compression libraries. There's over 115 packages that are now packaged together in this E4S software package. And all of them are enabled for accelerator-based computing. It's available open source to anybody who would like to make use of this software. And we think this is one of the main things that is allowing other agencies or our industrial partners to start to take advantage of accelerator-based computing because they have this software available to them. And so I want to point out that Mike Carew is our lead for the software technologies efforts within ECP, and he is a panelist on Friday morning. And so I would encourage you to attend that panel where they're talking about basically the state of the union for different software ecosystems. And he'll talk about E4S as part of that panel. And so a couple of last thoughts. I do want to point out that this was a large effort. We funded over 1,000 researchers to develop the software, develop the applications, and it was a unique collaboration that really brought people together from across the nation to build teams in ways that we'd never been able to do before. And we have found that sort of a sustained collaboration has just yielded tremendous benefits to the application teams, to the software technologies teams, and hopefully for our nation going forward. We've got a lot of best practices and lessons learned about using these kinds of systems, about building these sorts of collaborations. Happy to talk about any of those. And one of the things that we have made a particular investment in is the next generation. So not only did we fund 1,000 researchers to learn about accelerator-based computing, and now we've got a whole cadre ready to go forward, we funded about 1,000 students to introduce them to accelerator-based computing and just to high-performance computing in general. Lois McInnes has been leading our broadening participation activities, and she is giving one of the invited talks here at SC23 on Thursday morning. So again, encourage you to attend that if you're interested. And then I've made this point just briefly here. We believe the work that we have done will significantly impact industry and the other agencies through a lot of the investments that we have made to date in the software and our lessons learned and how we can teach folks, what sort of things should you be looking for as you're moving to an accelerator-based system. We have an industry and agency council that we've work with in the ECP. A number of those folks have made investments in frontier-like systems, and they're using E4S. And we talked to them about, imagine what's possible with 100x the compute power that you have now, but still in that same energy footprint that you have in your compute center, right? That's a really important factor for most of our industrial partners. They can't arbitrarily expand how much power they have coming into their compute floors. So again, highlighting something that's happening here at SC23, we put together a panel of some of our industry and agency partners, and that panel will be happening on Thursday afternoon, and they'll be talking about the impact of exascale and our project on industry. And so that might be a nice place to learn about some of the things that are going to be happening going forward. So my final slide, just telling you what I told you and summarizing. We believe that exascale computing, it's here, it's incredibly successful, and it'll have far-reaching consequences. The accelerator-based nodes that we can now effectively leverage at all scales, again, not just exascale, but also at, on the laptop, will significantly increase the amount of power, compute power, that's available to users within a given energy footprint. The performance improvements we've seen, they're not theoretical any longer. They are real. It's tens to hundreds to thousands with the right kinds of investments in the software and the algorithms. And then finally, that's already being used. Several of our applications have tens of thousands of users, and they're already able to leverage these kinds of investments that we've made. And with that, I'll say thank you and turn it over to Heather, I think is next. Okay.
Good morning. I'm Heather West. I'm a research manager at IDC, and I lead our quantum computing research along with Peter Rudin and Ashish Nadkarni. I'd like to first start by thanking the SC coordinators for inviting me here today to talk to you about quantum computing, specifically about some of the market and adoption trends and where we're going with regards to the utility of quantum. Imagine a world in which we had personalized medicines that could be used and prescribed to cure currently uncurable diseases. Or a world in which scientists and engineers could develop catalysts that could contradict the effects of climate change. Or the ability to design more energy efficient batteries, semiconductors, or other types of products. Today, we have limited capabilities due to the classical compute power limitations. However, quantum computing is expected to be the next industry disruptor, which will revolutionize the compute power that we need to solve some of these complex problems which are currently beyond our reach. Specifically, quantum computers are going to be suitable for solving problems that simulate natural processes, that optimize certain problems, and that are large factorization and algebraic problems. Because of its advantages, IDC has learned through a series of different surveys that the IT spend allocated to quantum is expected to increase. Up on the screen, what you see are results from one particular survey, and while there are percentages listed at the bottom, what I want you to take from this particular slide is the fact that we are starting to see an increase in the allocated funds for quantum across the different industries. For this particular sample, it was a sample population that was skewed specifically towards early adopters, so the percentages may be a bit high, but it's more the trend that I would like you to pay attention to. And why are organizations and enterprises investing in quantum? They're doing so to enhance their performance-intensive compute capabilities, specifically those related to HPC and AI. And they're doing this in a variety of ways, whether it be to investigate new problems or to extend the current capabilities of their current environments, or to integrate the two capabilities together, and perhaps even more innovative ideas and ways that we haven't even thought of yet. IDC predicts that by 2027, worldwide customer spend for quantum computing will reach $7.6 billion. However, the quantum computing market is going to be driven by investments into the technology. And these investments are expected to lead to waves of technological innovations and breakthroughs. Already, since the early 2000s, what we've seen is quantum computing as a proof of concept, an academic technology that has developed into small-scale NISQ quantum systems. However, as more investments get poured into the technology and its development, we're expecting over the course of the next 7 to 10 years that these systems will become more useful and we'll be able to use them for smaller scale problems at first and then larger problems as we advance towards the fault-tolerant quantum system. However, today, quantum computing is far from development due to the fragility of qubits that make up quantum computers. Currently, qubits are unable to scale. They don't have very long run times, and they have high error rates. However, once hardware developers are able to master and resolve some of these issues, we're hoping to have a universal fault-tolerant system that will be able to provide a quantum advantage. Well, what's a quantum advantage? If we think back a couple of years to 2019, Google announced they had developed a system that could reach quantum supremacy. And quantum supremacy was the ability to use a quantum computer that could solve a problem that a classical computer couldn't solve. But it didn't have anything to do with whether that problem was useful. And so, as the technologies advanced, so have our definitions of what this technology will be useful for. The fault-tolerant system, the most advanced system, is thought to be able to deliver quantum advantage, or the ability to use quantum systems to solve problems better, faster, more accurately, and cheaper than classical compute, in order to deliver a business and scientific value. However, to reach these types of systems, to deliver these types of systems, we need a high number of quality qubits, and right now that's thought to be over 1 million. We also need error correction that can be applied to these systems without interrupting the work that the qubits are doing. And we're going to need quantum networking, quantum sensors to help combine different systems, link different systems together. And these developments and advances, they're coming. There's many hardware vendors and hardware developers who are in the process of developing this technology, but it's still years out. And in fact, when we look at the screen, I've provided you with a list of both quantum hardware vendors and quantum hardware developers that are in the process of developing different modalities of quantum systems. The difference between the two groups is that while one group is still very deep into their R&D, the other group, while still performing R&D and conducting R&D experiments and such, have been able to develop systems and services and solutions and offerings that are available to enterprises and organizations to start experimenting with quantum today. However, as you can see, there's multiple modalities that are under development, whether it ranges from neutral atoms, trapped ion systems, superconducting, and more. And the reason for that is because it's unknown at this particular point in time if there will be a particular type of modality which will be more useful for different types of problems or industries, or if there'll be one type of modality which will reach quantum advantage first. We even have some quantum hardware vendors such as D-Wave, which is looking at different ways to use the quantum properties of the qubit in order to reach an advantage sooner. Up until the last couple of years, it was thought that we really needed to develop these systems to their fullest potential in order to get any sort of utility out of them. However, beginning in 2022 and continuing, we've started to see some research that's come available and some advancements in the technology that seems to suggest that perhaps we'll be able to gain some utility from these systems sooner than we even expected. In 2022, IBM and Q-Control started to develop technology, error suppression and error mitigation technology specifically, which helps to reduce the errors during and after a quantum computation is computed on the smaller scale systems that we have today. We've seen studies that various quantum hardware vendors have produced that seem to suggest that quantum systems, when measured against the capabilities of classical compute system, can definitely outperform the classical compute systems that we have that are of equal weight, equal performance. That is what we define today as quantum utility. Benchmarking quantum has been challenging just because there's so many different modalities. But what are we really interested in? What we're really interested in is having a quantum system that's able to perform better, faster, more efficiently, more cost-effectively than our classical compute systems. And these are what some of the research is starting to show today. Because of the quantum error suppression mitigation techniques that are being developed, we're starting to see some quantum hardware vendors announce that their systems will be able to deliver capabilities using over 1,000 qubits, or be able to deliver systems that can run in data centers or data center ready. By 2030, we have some quantum hardware vendors such as IBM and Microsoft, which are even suggesting that it may be possible to have a quantum system made up of over 100,000 qubits that can be used to solve some, not all, some of the most complex problems that we face today. And as these systems continue to scale, as the use and the knowledge regarding error mitigation and suppression and then into error correction keep advancing, the types and complexity of the problems that are possible using quantum to solve also will advance. For example, now we're in the purple. Our small-scale systems are only really useful for small-scale experimentation, and that's okay, because we need to be able to dive deep into these systems, be able to characterize qubits, be able to determine how these systems actually function in order for them to advance. However, quantum scientists, engineers, computational chemists, they want to be able to use them for more than just characterizing their systems. They want to be able to solve optimization problems that will be able to provide solutions better than what we have today. We want to be able to solve large algebraic and factorization problems that will help us develop and advance quantum machine learning, as well as help us provide, but on the downside of that also comes the problems that we have with cryptography. These systems are going to be able to break the algorithms that currently secure our classical data systems. Finally, the most advanced type of problems we'll be able to solve using quantum, those that will be able to simulate natural processes. For example, those types of problems related to quantum chemistry and material sciences. And as a result, what we're beginning to see is a growing use cases across multiple industries. And these are just a sampling from the manufacturing and financial services industry. But if we look ahead, the quantum problems that we'll be able to solve span all types of industries. And again, this is just an example. The list continues to grow exponentially as people continue to experiment with the technology. And as such, the era of useful quantum computing is approaching, the ability to use these quantum systems. Because we're seeing advancements with regards to the size of the systems, the scaled systems, modular systems being introduced. We're seeing a transformation from the focus and the emphasis of the quantity of qubits to the quality of qubits. At one point, all we would hear about is the number of qubits a system had. But it doesn't matter if you have 1 million qubits, if those qubits can't perform, if they can't stand, or if they can't have long coherence times. And as a result, we're seeing revised quantum hardware developmental roadmaps being introduced by different quantum hardware vendors. We're also starting to see the introduction of frictionless software that will help end users who are not quantum specialists use these types of systems. And we're also starting to see the introduction of scientific acceleration platforms which marry the knowledge of HPC, AI, and domain knowledge together so that we can solve problems easily, so that we can use all these systems in an optimized fashion. And as a result, there's a few things that we're advising that technology buyers to do now, because learning quantum takes a large learning curve. If a company or an organization is waiting until that fault-tolerant computer is developed to get a quantum advantage, it's going to be too late. So what we're suggesting is organizations just should start taking a look at these roadmaps that are being introduced to determine the needs that they have now and in the future, and how different quantum hardware developers are advancing their technology to reach those needs. We're suggesting that technology buyers should become active participants in the ecosystem, because there's many different organizations and many industries that are facing the same problems and challenges with the introduction of quantum into their organization. And we have a host of other different pieces of advice. However, now is the time to start investing in quantum, and not just quantum as an isolated technology, but quantum as a technology that can extend and act as a continuum of the HPC and AI environments. And so with that, I'd like to thank you.
Hello, good day. I'm Jack Wells from NVIDIA. We were invited to speak on HPC and AI, and so that's what we'll try to do in the next few minutes. Look forward to your questions at the end of this. So I think we're all aware that generative AI is growing rapidly. The large language models associated with the transformers are very much in the news and in the front of mind. It's interesting to reflect that the paper, Attention is All You Need, appeared on the archive in 2017. And this is the impact of this algorithm of self-attention to generative AI. As we think about science, as many of us are like to do, often science has a language. Science has a syntax and basically a structure that can benefit from transformer engines, and some of them are represented in the array of images we've displayed here on this chart. University of California, Berkeley produced a chemistry assistant to facilitate the design and synthesis of metal organic frameworks that can predict structures, and actually had a chat box interface that could advise on the chemical properties like the catalysis and reactivity, dramatically reducing the complexity of an otherwise overwhelmingly complex design space. Northeastern University has made tremendous progress with a large language model applied to DNA sequencing. They were focused on understanding the gene regulatory networks associated with non-coding DNA strands, so-called dark DNA. And this is an especially challenging problem because like proteins and DNAs, the context can be extremely large. If you were thinking about reading a book, the particular context that may be relevant for the phenomenon that you might find in the next chapter of the book. It adds to the computational complexity. And of course, there's, I think, a very fascinating and rapidly progressing project at Argonne National Lab that we're collaborating with and many others on understanding the large language model of COVID variants. Arvind Ramanathan is the PI for this project. We're collaborating with him. Interestingly, as they've continued to work on this model and advance it, they've taken the data from 2020 and tried to predict, if you will, post-dict, what COVID variants would have emerged. And they're finding tremendous similarity with actually the COVID variants that we've realized, you know, in our infection surveys. So that being said, we think that this is a big deal relative to the impact on science, and it will have a big impact in high-performance computing as well. As such, we are trying to learn from these leading scientists what the requirements are and deploy infrastructure that will support them. This is a story that came out in the lead up to supercomputing of a new record in ML-Perf for large language model training. And interestingly, Microsoft Azure and our internal bare metal NVIDIA EOS produced very similar results in terms of the score. So in the cloud and on-prem, the training of the large language model was within a couple of percent. The breakthrough, the infrastructure breakthrough that enabled this is basically an upgrade in the memory technology of our Hopper GPU, here shown in the HGX form factor. So we have a larger memory capacity and a larger memory bandwidth associated with HBM3E. NVIDIA has a history of trying to be as on the leading edge as possible of the memory technology as the technology advances. Here, the chart on the right shows that the HBM2 was introduced in the Pascal generation around 2016. Here we think about the introduction of the Pitts-Dynk supercomputer, for example, in the Swiss Federal Supercomputing Center. The A100, here was the HBM2E, think about Perlmutter. And now with the H100 and H200, we have HBM3 and HBM3E. So as memory capacity demands increase and memory bandwidth demands increase, we'll try to stay on the leading edge of that curve. Here, one of the announcements that we're making in support of this science is the Grace Hopper 200 superchip that has tremendous connectivity between the CPU and the GPU, the so-called chip-to-chip interconnect with 900 gigabytes per second of bandwidth and almost 5 terabytes per second of HBM memory. And big improvements in energy efficiency and performance on simulations like the quantum Fourier transform for quantum simulation or large language model inference algorithms. Another one of our announcements at this actually from this morning is that we were fortunate to be a partner in the announcement of the new Jupyter supercomputer at the Jülich Supercomputing Center. The new supercomputer funded by Euro HPC project. Jülich is the lead laboratory and the host, and we're partnered with Eviden and Partech on this new supercomputer that will provide over 90 exaflops of AI computing capability with about 18 megawatts of power. This leverages the Quad GH200 node design, which is a 4-way Grace Hopper NVLink interconnected board design that has a total of 16 petaflops of AI performance and over 2 terabytes of high-speed memory. This node description is being referenced by Eviden within their Bull Susquehanna HX300 liquid-cooled infrastructure that's being deployed at Jülich. And also with our partner HPE, the same 4-way node design is being leveraged in a set of other leading AI-focused supercomputers, notably CSCS in Switzerland, and the first deployment in the United States will be at Los Alamos National Laboratory through the Venado project. We see a strong trend here where HPC plus AI is rapidly advancing, And AI is becoming increasingly important in leading supercomputing projects. And basically all of these supercomputers that we are interacting with in the future are becoming HPC and AI supercomputers. And this chart tracks over time the AI flop capability associated with a series of supercomputers. So going back to Pitts Knight with like the Pascal series, that would be FP32. And as we move on to, say, the Summit and Selene area, we're still FP32. Now Perlmutter and Joules with the A100, we're referencing an FP16 AI floating point operation. And then more recently, we have, Leonardo, Mare Nostrum, and then the Azure and EOS machine I just referenced. Here it's FP8 with the transformer engines enabling very large increases in AI capability. And as we look into the future, there's a whole set of projects that are being announced this week that should come for deployment in 2024. That's going to provide us a total of something like 200 exaflops of AI capability in the near future. Los Alamos, CSCS, the Bristol UK AI project, the ULIC project, the TAC Vista project, the recently announced University of Tokyo, University of Tsukuba, JCA HPC Center is deploying the Grace Hopper technology, and so on. So this is a strong trend, and we think that it's going to grow, and we're very happy to be a part of it. So in summary, I would just say that we think AI is going to be a part of most supercomputing projects moving into the future. We think it's going to have a big impact on science. It's going to, at least it will have an impact in time to solution and energy to solution. And on the upside, we'll end up with qualitatively new capabilities for predictive capabilities that we didn't have before. And this is just a summary of some of the AI-centric press news that NVIDIA was a part of at this meeting.
So good afternoon. I'm Eric Strohmeyer. I'm here to give a brief overview of the top 500 and some of the results together with Jack Dongara and Wu Feng. 60-second list, yes. Blank list. It's 30 years ago that we started the top 500. So the first one at SC was actually in 1993. So it's been a while. I'm going to briefly present some of the highlights of the various top 10s for the different matrices, different benchmarks and matrices we collect together with Wu. I was going to talk about the Green 500. I'm going to highlight some of the changes we see in the structure of the list the last half decade, and how that ties into technological changes. And I'm going to highlight just the systems which entered the list the last 12 months. Because those are the real new systems, that's the new technology, and I want to give a highlight to that instead of looking back at systems which have been in the list for a long time. So this is the top 10, and the list is going to get public about right now. 1:30 is the official time. You see in yellow all the changes since June. You see that there are 4 new systems on the top 10, and 1 system was upgraded. That's a lot more than we typically had the last couple of years. The changes in the top 10, most of the lists, we only had 1 change. So there is a lot of change going on. And that actually continued further down the list, as I'm going to show on a different slide. We also had a fairly substantial number of new systems in the top 50 overall. So that's nice to see. Of course, the big news here is the number 2 system, Aurora, system at Argonne National Labs, which is supposed to be in the final, in its final size, in its final installation, a 2 exaflop system. Aurora is being commissioned right now, so they submitted a measurement based on half of the system size. With that, with an early measurement, they still could get the number 2 spot. So that's quite impressive at this point and should move up further. So it's questionable if Frontier is going to stay the number 1 system for much longer, but it has been the number 1 for a while and still is. It's the only exaflop capable system on the list right now, which we know of. The ones we don't know are not on the list, obviously. The number 3 system is remarkable because it's the highest ever ranked cloud system, the highest ever ranked commercial system. It's a Microsoft installation at Microsoft Azure. I understand it took some convincing internally that they actually came out with this measurement, but they did. It's very impressive. It highlights a couple of different things, one of which is actually that the concentration towards very large systems, very few very large systems, and much smaller number of medium-sized systems, that concentration which we have seen in the research market for quite a while, that is happening in the commercial market just as much. And the high concentrated systems, the very large systems in the commercial market tend to be cloud systems. So this is one example for that. It's a very nice achievement with Microsoft being number 3 in the list. Lumi, one of the Euro HPC systems at position number 5 now, was upgraded again, but it was a minor upgrade. It didn't lead really to any reshuffling in the list. It's number 5 now. And there are 2 more new systems, another Euro HPC system in, I believe, in Barcelona, the Mare Nostrum system in Spain. And a second commercial system, and this time instance of an NVIDIA system installed at NVIDIA itself. So I'm not sure they're going to call that a cloud, but it is a commercial system in my opinion. So nice changes in the top 10. There is life in the list this time. If we look at the HPCG, top 10 for the HPCG benchmark, which is one of the 3 benchmarks we are tracking right now, all 3 of which, by the way, checked, developed. So the conjugate gradient benchmark we're using is a much tougher benchmark. That's why a lot of the systems are hesitant to submit numbers or haven't given us numbers for whatever reason. We have about 113 systems in the list for which we have a measurement, and it's slowly growing. So it's nice that it's still growing, but it's not complete. That's why some of the new systems you saw on the previous slide, in particular the cloud system, the commercial systems, those systems don't tend to submit HPCG numbers, and they are not on this table. So that's why on this table there is much less change. The last system is remarkable because if you look in the second column, you see where that system is in the top 50, in the top 500, and you see it's in the top 500 actually at position 50, but its architecture is so geared towards memory access that it allows it a very high efficiency on the HPCG benchmark. So that traditional vector system from NEC with that was actually able to get into the top 10 in the HPCG benchmark. So that's HPCG. The other benchmark check developed recently is the mixed precision benchmark, which was inspired originally by AI algorithms, which were the first ones to really, or some of the first instances of algorithms which used mixed precision. And check showed you can do the same thing for linear algebra and for scientific computing. And what this table really does, and it's a much smaller table, what it does, it really demonstrates the power of these mixed precision algorithms. The column in the middle where we show the HPL MXP score, that score is not an actual measurement how fast the system runs. It's a fictitious number based on how fast the 64-bit traditional supercomputer would need to run to keep up with the system running the MXP algorithm. And that's quite impressive because those numbers typically tend to be way above the peak performance of the system on which they actually were executed and operated. So that table is really a motivation for the community overall to look more into these algorithms and use these algorithms to speed up execution of code more than increases in speeds in hardware allow. So with that, I want to turn it over to Wu, who's going to talk a little bit about you want to do the Green 500?
I was going to
Okay. So Green 500 is a technology-based ranking where we don't rank systems by size, but by how efficient they are. So we typically have a lot of the smaller systems on there which are geared towards high efficiency. So being a technological oriented list, we have usually a lot more turnover on the Green 500 than on the top 500 itself. This list, everything is upside down. We have a nice changes in the top 500, but the Green 500, the top 10 in the Green 500 didn't change much at all. Probably because some of the new systems weren't measured, just like cloud systems, commercial systems don't tend to measure, don't provide these secondary metrics to us, so we don't know about those systems. And probably also because a lot of the matrices, a lot of the new technologies were introduced in smaller systems 6 months ago, so we didn't have as much turnover this time as we usually have in the Green 500. And Green 500 has its own BOF session on Wednesday. And sure.
So thanks, Eric. So as you can see, the top 500, the top 10 of the Green 500 list only has those 2 new entries. So there's less churn on this list as in versus previous lists, and that 5 centers have now reported energy efficient optimized runs, and those are denoted by the asterisks, which is also an improvement over the past lists. It should be noted and highlighted that at number 8, that's the only actual exascale supercomputer that has achieved exascale computing in 20 megawatts, which is what the DARPA exascale study was putting as the bar back in the mid to late 2000s. So exascale in 20 megawatts is a lofty 50 gigaflops per watt. Okay, which you can see that there are, of the top 10, the top 8 are the ones that have reached the 50 gigaflops per watt threshold. But again, it's only Frontier that has actually achieved the exascale with 50 gigaflops. The other 7 that are above, which they've reached that lofty barrier of, or goal, I should say, of 50 gigaflops per watt, those you would have to extrapolate out to exascale supercomputer to reach exascale. Let's see what else. So in spite of this lack of churn in this edition of the Green 500, I think the future of Green HPC is still looking quite bright, though there may be at least one worrying trend from a logistical and operational perspective that I'll address briefly. On the brighter side, I think we're seeing that Green HPC is becoming increasingly global and arguably even self-aware as a logical extension to the IM HPC theme this year at SC23. And that's evidenced by 8 different countries in the top 10 of the Green 500. Okay. So the US is at number 1, number 2, and number 10. And then in the intervening spots, starting with number 3, it's France, Australia, Sweden, Spain, Finland, Germany, and South Korea. And if we extend it a little further, we have Japan popping in at number 12. Secondly, in terms of the brightness of the outlook for Green HPC, there was discussion about quantum computing, which is closer on the frontier than we may have originally imagined it. It's something to note is that because of the extremely low temperatures required by quantum computing, the power consumption of the cooling system is likely to be much greater than the actual power consumption of the compute resources itself. So it's something to keep in mind. So with the brightness of that outlook, I'd say that there's one worrying trend that I was referring to earlier, is that while the broader interest in Green HPC has hit its peak in the early to mid 2010s with 324 submitting systems, it's since dropped to about 200 systems. So there's less reporting that's being done, which would circumstantially indicate that there's lessening interest in Green HPC. But on the other hand, I I'd say that if we look at the Green 500 BOF, which Eric has referred to, it's on Wednesday at 5:15 to 6:45 on Wednesday. The attendance and feedback on the Green 500 continues to be quite high, including discussions on simplifying the run rules while simultaneously increasing the rigor of the measurements. That's kind of conflicting goals. It's hard. It'll be hard to do that. And then the second thing was, and it's been brought up by Jack, Mike Hero with HPCG, as well as the folks from the Green 500 BOF, about looking at HPCG as a workload with respect to evaluating the energy efficiency of Green 500 supercomputers. Right, that's it.
Thank you. Quick question, how much time do I have left? Another hour? 30 minutes, okay. So I'm going to be quick. How many new systems are on the list? 45 systems left the list at the end because of size. That's historically very low. That's related to the systems in the list getting much, much older. That's a trend which continues and there is no end in sight. On the other side of the coin, when we look at performance, of course, with Aurora and Eagle, the number 2 and number 3 system coming into the list, there's a fair amount of performance coming into the list. So that looks nice, and it would be even more if we had the full Aurora system. But having said so, what that reflects is that at the high end, we accumulate more and more performance off the list in the high end. And now if you calculate how many systems you need to accumulate half of the total list, it's only 7. So the first 7 systems on the list have as much performance as all the 493 remaining combined. So that's quite a bit. It's a trend been going on. If you look at performance growth has fallen off the last couple of years. We see 3 inflection points. The first 2 are related to the end of the NAR scaling in the mid-2000s. We know that. There is a new one in 2017. How drastic that fall off is, John Shelf, a colleague of mine, visualized that nicely. The old rule based on Moore's law was within 11 years we would gain a factor of 1,000. That has come down to now a factor of 2 or 3 or 4. So it's dramatically different in terms of growth rates, what we are seeing in the list. And if we just take that last curve since 2017 and project that out, we see that if we are lucky, but only if we are very lucky with the way we do business right now, we're going to reach 10 exaflops by the end of the decade, and even that is not a guarantee. So performance growth has slowed down quite a bit, and we need to change how we approach things. Here I show that the next 10 systems which are new on the list in the last 12 months, and I show that just to show the variety. First of all, 10 additional systems, new systems between position number 10 and 40 is actually quite substantial. The first one came in June, the remaining 9 came in this time. Last time we had 1 new system in the top 50. So that is quite nice to see that many. You see it's a mixture between commercial systems and research systems, and geographically they're all installed in a much more diverse mixture of countries, including Asian countries and Saudi Arabia and things like that. Technological-wise, these are also very different systems. And on the note of technology, I forgot to mention, and I don't think there's another example here, is that the Aurora system is special because it's the first system which uses really the Intel Sapphire technology for CPU and GPU, and that's a new type of system which has made a strong entry this type of list. Okay. So our countries, United States, clearly the leading consumer. China looks like it's number 2, but that's based on older systems. If you just look at the systems which came in this year, you see United States is clearly the leading new installer of systems, followed by Germany, Japan, and other countries. And you're not going to find China there, because China is under others. China submitted only 1 new installation within China, if I saw the list correctly. So we're not getting numbers anymore for how many systems are installed in China. That's for political reasons. We don't get that. That's very clear. Okay. Where these systems actually produced? Now, obviously, on the left-hand side, China is all of a sudden there. And if we drill down, well, in terms of number of systems, well, in terms of performance, for the last year, the last systems in the last year were mostly produced in the US. If you drill down into what are these companies in the last 12 months, we see that the Chinese company which produced those 38 systems is Lenovo. It's Lenovo only. The others, we don't know numbers from the other companies anymore. And all but one of those Lenovo systems are installed outside of China. So we get the Lenovo installations from outside of China. We see those. Most of those, over 30, are installed in the US. 3 in Germany, and then 1 in South Korea, one in Argentina, and 1 somewhere else. So it's one in China. So it's Lenovo is selling systems very successfully, at least at the lower end, at least in the commercial market. On the right-hand side, you see the influence from the number 2 system, Aurora. That's the Intel slice, the Intel Sapphire technology, the red one, and the blue slice is the Microsoft Azure systems, which contribute a lot of performance. That's why they show so dominantly on the right-hand side. In terms of technologies, those 91 systems, I'm almost done. Those 91 systems are almost, in terms of performance, most of them use Intel as main processors. In terms of pure numbers, about half use Intel as a main processor and half will use AMD as a processor. You might wonder why, for instance, ARM doesn't show up here more prominently. The big system, the big ARM-based system is Fugaku, and that is older than 1 year, and these are only the systems from 1 year. So also, for instance, Frontier is not included in the statistics because it's older than 1 year. So this is really last year. And here you actually see the influence on the right-hand side, the big influence of the Intel Sapphire technology in the Aurora system, so the Intel Data Center CPU, which is used in 4 systems. The CPU, the main processor, Intel Sapphire, is actually used in 25 systems, so that's a lot more. So to summarize again, Frontier remains the only known exaflop system to us. There are 4 actual new systems in the top 10 and 1 upgrade, which is a very nice and unusually large turnover. There is additional 9 new systems in the top 50. That's also much more than we have seen the last couple of times. In terms of new chips coming onto the list, this last list, and especially this list, is clearly the Intel Sapphire CPUs and GPUs. We use our systems much longer, they get much older. That's due to a couple of technological limitations which forced us to change our buying behavior. That's an effect which we see not only in the research market, but also in the commercial market. And hand in hand with that goes a concentration towards very large systems at the top. And now in the commercial market, we actually finally see, after we've gotten that question a lot of years, a decade, where are the cloud systems? We see that they are there. They're a little shy, but they are there, and they are the very large systems at the top of the commercial market. The end of Moore's law is coming. There is no doubt about that. We see it in weird ways. I believe that a recent slowdown since 2017 is actually more based on our inability to grow systems macroscopically. Our data centers cannot go much larger than they are, so we cannot increase the number of nodes, the number of CPU sockets. That's a main limitation since 2017, but the end of Moore's law just comes on top of that. And unless we change how we approach supercomputing, our growth rate in the future are going to be substantially smaller than they have been in the past. Thank you. So do we have Q&A now?
Sorry, we're getting the mic set up.
Yep. Just don't know if I amplified.
Thank you so much for all this information and your time. If anybody has any questions for anybody, I can, thank you.
Hey, Lori, I wanted to ask a question to you because there's a couple different announcements that kind of are confusing me, right? So there's the E4S, which you spoke about, but then I saw today about Linux Foundation had the High Performance Software Foundation. Are those competing standards? Are those complementary? Can you explain that?
I probably can't explain it in as much detail as you would like. There will be a kickoff tonight at the DOE booth in the gala at 8 p.m., I believe is the scheduled time, so I encourage you to go meet with the leads there. But a lot of the software products that are developed as part of E4S are also a part of this foundation. And so many of the early products, so SPAC, AMRX, some of our application teams like WarpX have all agreed to join the foundation. And so they're more complementary than they are competing.
Hi, Ian from More Than More. Top 500 system. I know there's nobody from Intel here on the panel. Just wanted to get clarification on that Aurora submission. I believe you said it was half of the full system expected, but still expecting 2 petaflops at full scale. That would make it almost 100 megawatts. So can you speak to any optimization that they may have said with their submission and stuff? Or is it a typo?
I don't have the Aurora power measurement on the top of my head. I believe the total Aurora system would be more on the size of 50 or 60 megawatt, not 100, so I don't think we are close to 100. But it is more than Frontier, for instance. The half system of Aurora, I think, uses a little more power than Frontier, 5 megawatt more.
Yeah, I'm just scaling up to 2x, and I get 100 power. So I'm wondering if that power number was a typo.
No, so I think the power number was 24 megawatts. That was in the table, 24 for half of the machine. The machine is fully populated, so I'm not sure exactly where they're measuring things. But there's the network involved, and there's cooling and all sorts of other things which are active, even though it's not being used, my guess is. So I don't think it's quite 100 megawatts. I think it's closer to 40 megawatts.
Yeah, that makes a lot of sense. Thank you.
Probably doesn't double,
Yeah.
In the worst case, they gave us the power
quadruple.
number for the whole system, running only half of it. So.
Yep. Thank you.
Thank you. Just a question for you. It sounds like next year Lawrence Livermore is going to be putting up El Capitan. Just wanted to get your perspective on, the build out, and also just do you have a sense of where you expect it to kind of fall out on the top 500 list? I think there's some expectations that it's likely going to displace Frontier.
It's your machine.
The question was for the top 500.
Okay. So if it's for the top 500, when LCAP is online, becomes available, it most likely will be the #1 machine. Exactly when that's going to happen, though, is something that's a bit vague at this point, as the machine is just starting to become populated and starting to go through its test cycle. These are complicated machines, and they take an enormous amount of effort to get the hardware, the software up and running and optimized. So don't hold your breath for LCAP.
So on a related note, just to explain, in case you don't know HPL, HPL is a very demanding and a very precise code. So you might be able to run a lot of codes on a machine before you can actually run a full HPL run to completion with correct results, because virtually nothing can go wrong. That's why I would think once a system has a successful full-scale HPL run, it's ready for general usage. So it's not surprising that a system, for instance, like Aurora, doesn't submit HPL numbers soon after they built it. There's a lot of shakeout which needs to go on. It's going to be the same for El Capitan, and they might run some codes before they're actually able to run a full HPL run.
George Kozma from Chips and Cheese. So with regards to the Green 500, there was comments about how less systems are being uploaded to the Green 500, but I'm wondering about the trend of how much more energy efficient have we been getting over, say, the past decade or so.
So The top end of the list has been getting significantly more energy efficient at a faster rate than the rest of the list. At the Green 500 buff, we traditionally will show the trends of the energy efficiency of these systems relative to the top end and the outliers to the middle, the two middle quartiles and toward the bottom of the list. If you look toward the bottom of the list, the improvement in energy efficiency is basically flat, it's linear, versus the more exponential improvements that we've been seeing at the top end of the list. That being said, when we started the Green 500 about 16, 17 years ago, we deliberately keyed off of the DARPA exascale computing study, and we showed that the energy efficiency of supercomputers back then, when extrapolated out to exascale, was on the order of several gigawatts, or several thousand megawatts. And as time has come over the past 17 years, we've been able to get that exponential improvement with respect to getting all the way down to less than 20 megawatts for an exascale supercomputer.
Thank you. Vladimir Kozlov, light counting. This is a question for NVIDIA. I think it was Lori's presentation that mentioned the benefits of systems designed on combinations of GPUs and CPUs. By looking at the latest NVIDIA designs, it seems like the trend is interfacing GPUs directly to each other and kind of leaving CPUs on the side of the system. Is that first of all, if that's correct or not? And second of all, is that a general trend, or are there specific tasks, specific models that benefits from very large GPUs arrays?
Let me take the first question and ask you to repeat the second question. So what I presented and focused on mostly here today was the Grace Hopper Superchip, which has a very large, radically limited CPU with 72 cores, very high performance and very energy efficient, coupled in a high bandwidth manner to the GPU. So, no, the CPU is very important, especially for the large memory bandwidth demanding AI models and complex multi-physics simulation models that are that have some components that are running well on the GPU and some running well on the CPU. And these are very well oriented for a programming model with enhanced automation to handle some of the complexity. So I think I don't agree with your summary statement that the CPU is not important and it's all about the GPU, if I understood your question correctly. Did I get it right?
Yes, yes, but more specifically, if you look at your EOS system, it has a lot more GPUs than CPUs, if my understanding is correct. And it also has a new network, the NVLink network, that's based on optical connectivity, that for the first time connects GPUs directly in a very large array using optical interconnects. So I'm just wondering if it's a trend that we should see in the future, is going to be specific to some of the models that NVIDIA is running.
I don't think NVLink is optical. It's not an optical
It
memory.
is.
Yeah.
It is.
So let me cut this a different way. If you take a look at Frontier and take a look at where the performance is coming from for the benchmark run, you get 99% of the performance is coming from the GPU, 99%. So the CPU is only really there for the communication part of that computation. Now, that's only one computation. Real applications, of course, may vary.
So I'll comment on the real applications. We are also seeing most of the performance coming from the GPUs, but having that tight coupling right now between CPU and GPU has been very effective for our applications. And my impression is, as we go forward, that connection will remain very tight and will become easier and easier to program. And so that's going to be a big difference for the adoption of these kinds of technologies too.
I would say if you have a code that's evolved, for example, from Titan to Summit to Frontier, it's evolved to be GPU resident, where most of the memory is on the GPU already, and they've limited the data movement. But for a broader set of codes where there's more complexity, the high bandwidth interconnect between the GPU and the CPU will be very valuable. And the reason that the EOS has the x86 plus Hopper is because Grace Hopper is now just being deployed in 2024. Grace Hopper is only becoming available now.
Roy Rubenstein from Light Counting also. A couple of years ago, you gave some insight into what was happening in China. Is that dried up? And then another question is, if you extrapolate to the next 10 years, and you said maybe just a factor of 10, what does that mean? Is there any visibility of how this could be improved, or is it just these larger systems are going to slow down, relatively speaking, and supercomputing is going to become more dull?
Let's see, I have no new information about China. David Kahaner, is he still here? David's gone. So David is the expert, and he just left the room, I guess. Good timing on his part. Let's see, and then the other question is about, we've had these major changes that have taken place over the 30-year lifetime of the top 500 list. We had single CPUs, we had multi-core, we had vectors in there too, so let me not forget that. And then we had CPUs and accelerators, and we're waiting for the next magic thing to happen. I don't know what that'll be to help accelerate again how high performance computing goes. So I think we're waiting for that.
So the only thing I would add is that next magic thing might not necessarily be hardware again, like in the past. It might actually more be related to software, to things like mixed precision algorithms and stuff like that.
Yeah, that's a good point.
That's why it's important for us to keep up with how to actually measure what HPC is and does. So the traditional HPL might not be sufficient at some point to capture that.
With HPC Wire, this question's for Lori. How do you plot advances in building supercomputers? Right now it's GPU, CPU. Do you see it consuming more power as you go forward? And is there an alternative way in which you proceed with pushing the sort of performance envelope without affecting the power?
So many of the investments that we've made in our algorithmic improvements to take advantage of accelerators, we're seeing early results. So I think it was mentioned, maybe it was Jack, mentioned the ideas of mixed precision and starting to leverage that more and more and more for scientific computing. So that can sort of reduce, the power consumption and significantly accelerate computing, reduces memory bandwidth, all of those good things. So I think that's one trend we'll see. Another trend that we are increasingly seeing, and this is the focus of Jack's talk, was the incorporation of AI into these large multiphysics models. They're serving as surrogates in many cases, and so significantly speeding up, key kernels of computation. And so, from our perspective, one of the things we're really looking toward are some of these algorithmic improvements and broader incorporation of those kinds of technologies to accelerate applications while keeping the power footprint manageable.
I'd add, supporting what Eric and Lori have pointed out, is that I think the big frontier is software in terms of getting the better performance as well as energy efficiency, and we're already seeing with these growing energy envelopes that there are some data centers out there right now that are not charging or providing quotas in terms of CPU hours. They're providing quota in terms of energy usage. And so then that in turn will arguably force the application writers to write new software that's more energy efficient while still being performant.
So if I could add one thing. So earlier in one of the presentations, it was noted that quantum, the energy needed to cool the system, is fairly high. And that is not incorrect with regards to the superconducting system, but that's being worked on at this particular point in time. But with regards to this particular conversation, quantum going forward, using circuit knitting and circuit embedding techniques is thought to be a way to integrate quantum into HPC and AI so that you can optimize the code for those problems that are the largest, most complex problems that will go to quantum. You'll send others over to the classical system and then knit them together at the end so you have the most optimized system. And in that particular way, how to reduce some of the energy that's being used by some of the supercomputers in HPC. But that's a long way in development, but the software to do that is under development today.
Hi, Felix with More Than More. So one of the topics that was brought up in the first, one of the first presentations was algorithmic efficiencies and increases in performance that way, because hardware is increasing in performance, but software is where our main limiting factors are these days. With that, there was a point made about 10 to 100 to even 1,000x performance increases over time. A lot of that is recent research with, hey, we're running out of memory bandwidth and we need to move to lower precision, mixed precision, reduced precision. But the other point made was fundamental algorithmic shifts. And I was wondering if you might be able to speak to that. Is that new numerical methods research, or is that just we have old codes written in F77 that need to grow up and move to F2018?
So I have a talk that I've given in the past that is what's old is new again. And one of the things that there was a lot of research on, I don't know, 20, 30 years ago, Jack knows this, were like high precision algorithms. And at that time, for those architectures, they were deemed not very effective, not very efficient, too expensive. What we're seeing now is with the shift to accelerator-based systems, you really want things in residence. So high arithmetic intensity, like high order discretization schemes are now really paying a lot of benefits in terms of bang for the buck in increasing the accuracy and effective use of these machines. So I think we're going to see, there are some codes that are still written in Fortran 77 and they are out there, but we have a lot of codes that are pretty high performance on the systems of 10 years ago that are actually revisiting algorithms. In fact, the small modular reactor example I gave was one of those that turned its algorithms on its head. When you're tracing particles through these fuel cells, you used to do it on a particle basis, and that had a lot of decision points. If this particle is doing this, then you do X. And what they're doing now is they flop that, and this again was an algorithm that was looked at 20 or more years ago, flopped it on its head and said, well, let's look at it on all particles that are have this kind of an event, we're going to group those together. And that's much more effective in terms of utilizing the GPUs because it doesn't have all the decision points. So I think we're seeing a lot of that kind of activity in the algorithm space too.
Sort of a piggyback off the previous question. With regards to the newly announced AMD MI300A, do you think that sort of moving both the CPU and the GPU essentially into the same memory space is a game changer for not just older HPC codes, but also newer ones that will come along starting from now?
Yeah, I think locality is always going to be important, right? I think where that's really going to help. So if your code doesn't have a lot of locality in it, I think you're going to need to do that work. But what I'm really hoping we'll start to see are programming models and the ability to access these different memories a lot more seamlessly, potentially, than we've had to over the last, say, 10 years. And we are starting to see that with different programming models and tools that help with performance portability, not only, CPU, GPU, but also across different kinds of GPUs, right? So a lot of the investments that we've made with the exascale computing project, we're hoping will help future-proof a lot of these codes by sort of extracting out those layers that are really specific to the different kinds of hardware and allowing them to be more performance portable with less work. And we already see evidence of that right from previous, porting from NVIDIA systems to HIP-based systems or sickle-based systems. went from years of effort to do that to just a few months, right? And so those kinds of achievements and, you know, developer productivity, et cetera, I think we're going to see a lot of that on the software side.
Okay, we're going to do 2 last questions here and there. Thank you.
Thank you. It's a question for Heather. Vladimir Kozlov, Light Counting. Is there a top 10 list of quantum computers? If not, is that the right time to start one?
No. And the reason for that is that quantum is still really early in its development. And so the quantum hardware developing companies that are working on these systems, they have very few systems available to begin with. So IBM leads where they have a fleet of over 20 systems available and up and running that you can go and experiment on. But other quantum hardware vendors, they might have 1 or 2 systems that they're working on, and as a result of that, the availability and accessibility is somewhat limited. But hopefully, as time goes on and it advances, we'll have a top 10, and we might even have a way to benchmark the capabilities and differentiate them in much the same way that we've seen here today.
Seems like the last question is no longer a last question. Does anybody have a question? Yes, you do. Patrick.
Yeah, I got an easy one. Hey, so I guess the easy question, you know, how do you fix the top 500? You know, you have a Chinese vendor that is submitting over 1/3 of the results that are, you know, internet provider A at site X, and then they have, you know, this set of systems, the next set of systems. So, I mean, really your 91 systems new this year, that's over 1/3 of that is web servers, right? So like, how do you fix that? Because you have less than 60 new systems that are like really doing HPC work on the list. So like, how do you change that? Is that getting HPE, Supermicro, Quanta, all these guys to start submitting their web hosting clusters? Is it, you know, measuring things differently? Like how do you change that? And you have all these AI systems that clearly could be on this list, but that aren't submitting results. So like, how do you fix that? Easy question for the last one, right?
It's a long-standing problem, and the start of that was actually a decision we took in the 1990s, early 1990s. IBM had the SP parallel systems, and they sold them very successfully to commercial customers. And we said that there is a supercomputer, and we wanted to have it in the list. So we said commercial customers are allowed. We just have a rule that we like to track the systems, so they need to tell us where it actually is, even if officially it's anonymous. So we can track where it is and so on and so forth, avoid double submissions and stuff like that. And of course, companies have become very successful in selling those. So the fraction of those systems, especially the anonymous one, has grown too large, yes. How can we fix that? I would actually put a different spin on it. What I think, what is cumbersome with the list right now is this development that there is fewer and fewer new systems per edition. So we look at a collection which is fairly old, on average 3-4 years old. So to change that, I start publicizing more statistics about new systems only. I also do statistics where I look at research market only and commercial market only. So if you're really interested in those numbers, you can go through the full set of slides I'm going to show tomorrow. And there are the slides in there where you see how the research market develops, who sells in the research market, and so on and so forth. And that gives you, for a pure traditional HPC focus, that gives you the numbers you want. Because I try to do it clean. I do a top 100 research only. It's not as highly visible, publicized. You could, for instance, put up spreadsheets on the web where only the top 100 research systems are in there. And for those people who are really only focused in that corner of the market, they see that. You wouldn't see something like the Eagle system or like the NVIDIA system on it because they're commercial systems. So you would miss that, right? Even if that Microsoft Azure system is a cloud system geared towards HPC, you wouldn't see it because it's a commercial system, it's a cloud system. It's not different from any of those 30 systems Lenovo sold.
Well, what do you do? Like, I mean, there are so many AI systems out there that could make that list if they ran LinPack, right? I mean, so I guess that's kind of the question. Like people literally have these accelerated systems that can go run this and get on that list, and that interest isn't there. So how do you jumpstart that interest?
So before I let Jack answer that, if you look at number 11, is the highest ranked AI system. That's an example for if the company wants to do it, they can do that. It's really at the end of the day, it's their problem, not ours. Right?
I guess I would suggest removing a 0. So instead of having the top 500, we really look at the top 50, and those are really the, quote, scientific supercomputers that we're interested in looking at, and the other machines are not really part of that scheme. I'm not saying throw away the top 500, but let's have another list that we more focus on in terms of, I'll call it real scientific computing.
All right, well, with that, I would like to thank everybody for coming and thank all of you for speaking and answering the questions. I will bring your attention to the fact that we misspelled Wu's name in the brochure and on the table tent. So please disregard that. Absolutely unintentional, and I'm very sorry about that. And then to finish, I do have some exciting news. This is going to be the first time ever at SC that we are going to be offering the press a private tour of the SciNet NOC. So I highly encourage you to take advantage of that. It's going to be a short tour. No pictures will be allowed inside the NOC because most of the things are still in form of prototypes, but I think it's something that you should all take advantage of. To do that, we will meet here at 4:30, just 4:45 or, yeah, around that time. And then when everybody's there, we'll bring you upstairs and get you to the tour. All right, thank you very much.
If you haven't already, please go ahead and grab a box at the back of the room. Some lunch is provided.